Welcome to Hadoop Training. My name is Richard Kirshner with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. Please feel free to add comments down in the YouTube video as we do track that, or visit us at our website, www.simplilearn.com, and follow us on our YouTube video channel. What's in it for you? Today we're going to cover the need for Hadoop, what is Hadoop, Hadoop ecosystem, Hadoop features, what is HDFS, what is MapReduce, what is Yarn, and we're going to jump into a bank case study where we'll do a basic Sqoop setup in the Hadoop file system. So it's always good to investigate what is the need for this new tool, what is the need for Hadoop. And it's not really a new tool, it's been around for a number of years and it's been highly developed and it's very stable. In today's world, data is increasingly growing from heterogeneous sources like social media, aviation, logistics, and e-commerce, etc. And you can see here a number of examples with the little icon for Facebook and Twitter and Amazon. Coffee cup up there, I guess they're tracking how much coffee you drank that day. One of those machines that recommends stuff for you when you show up at the coffee shop. All this digital data is expected to reach 163 zettabytes by 2025. And remember, 1 zettabyte equals 10 to the 9th terabytes. That is massive. If you have a high-end desktop computer today, you might have 1 terabyte on that computer. So that's like having 10 to the 11th of those computers storing all that data across the world. Companies face problems in storing and processing these vast volumes of data. So if you're going to collect this data, it's a good idea to be able to use it for something, to analyze it and to help both your logistics, your sales, your marketing. Just about everything in business nowadays can use some basic data analysis to help them out and help them best serve their customers and be profitable. So the solution is big data technologies such as Hadoop. There are other technologies out there. Hadoop just happens to be the forerunner for both price effectiveness and stability. So Hadoop is one of the top solutions now for storing and processing big data. What is Hadoop? Hadoop is an open source framework to store and process huge volumes of data. It stores large volumes of data in multiple data nodes. You can see here we have our data coming in and then it splits it across. You could think of these, each one of these nodes as being its own server. Now the node is a container on the server, so you got to keep that in mind. You can create a pseudo node with multiple containers on one machine, although the purpose of it is completely void at that point and you use that for testing. So you can think of those each as being their own server, and then you can have racks of servers and so on, so it's completely compartmentalized across multiple servers. And it processes data in parallel in multiple data nodes. And this is important. And we'll mention just a minute here on some of the ecosystems, how it varies and how it processes data and how that looks. But this allows us to scale up in a linear fashion across many computers to process our data. So let's look at some of the basic components of Hadoop. The first component is, of course, the HDFS, the distributed data storage itself. The second major component that goes on in the backside of Hadoop is called MapReduce, or parallel data processing. The basic MapReduce is programmed in Java, although you can access it from other platforms. And Yarn is your cluster resource management. How does it keep track of where all that data is and where it's going and what processes are going on? So let's take a look at the Hadoop ecosystem. This is just a flash of the components on the Hadoop ecosystem. So we have like our workflow with Uzi. We have our Apache Zookeeper for management and monitoring. We have scripting languages, an SQL query with Pig and Hive. We have Apache Drill for interactive analysis and Mahout for machine learning. And we'll point this out in just a minute. Spark is kind of replacing Mahout, but Mahout is still very highly used in a lot of areas, and there's a reason why those two entities are separate. Spark is actually its own container, so if you have Spark on top of Hadoop, Spark is running separate, but it interfaces with Hadoop. And then we have Kafka, Apache Storm for streaming. We have our Apache HBase read-write access to data. That's your NoSQL, so you have families and stuff like that of columns and data and stuff like that. And of course, we have to have other ways to get our data into the database, so we have things like Sqoop, which we'll look at later on in our case study, and Flume. These are just for collecting the data and bring it into the Hadoop file system so then we can ingest it and analyze it. And this all sits on top of our Hadoop or our HDFS, Hadoop Distributed File System, which is run by Yarn, our cluster resource management, and then we have our MapReduce, which is the backend for the data processing. Understanding MapReduce when you're looking at the Hadoop ecosystem and big data is very important. One of the best advices I received from one of my mentors was it's not just about learning MapReduce, it's about thinking in MapReduce. So even if you're using one of the higher end scripting languages on top of this, still understanding how MapReduce works and why is very important. So we kind of hinted at why Hadoop earlier. Let's dig a little deeper into the Hadoop features that makes it so robust as a growing tool in data analysis and data storage. The first thing is it's very flexible. If you remember from our Hadoop ecosystem we just looked at, we talked about SQL, we talked about NoSQL, you can store documents, you can store just anything you can store on your personal computer, you can store in the Hadoop file system. So it's very flexible. It's very scalable. Unlike processing on a pure enterprise computer system, with Hadoop, you'll still have an enterprise computer for the master machine that's looking over everything. So you still can't get out of that expense. But then the rest of the computers are commodity machines. They are, one of the people I work with describes them as the computer on your desk is a commodity machine versus a very high-end server. The best description I ever heard was it's a bunch of knockoff machines, Chinese or Taiwanese knockoffs, or, from anybody who's building these computers, and they throw them together, and you're not expecting them to be, you're expecting to lose a couple of those computers when you order 50 of them, but you get them at dirt cheap prices. Because of the way it's built, it's very fault tolerant, meaning that it has replication of the data, it tracks that replication, so if something goes down, it's very quick to spin it back up and keep it running. Very fault tolerant. It's a distributed storage, so we're distributed across multiple computers. That goes with the scalability. It's a very robust ecosystem. It's got a lot of stuff developed on it over the years, so it's now very useful for many different needs and niches. And the big one, this is what you go to your shareholders and you say, hey, we have a huge amount of data that's stored on old tape backups and weird backup drives that you can't access. So we're not even using it for our analysis to know what our customers need and are doing. And we have some high-end computers which have the current stuff which we can access, but they're being used for the ongoing data business. Why don't we put all that stuff into a Hadoop file system, and then we can use that to power our analytics for our company. So as a big bank, we can now know who to give loans to and how to properly put them on that list, that we can give 1% to this group, and this group is automatically allowed through for loan applications and that kind of thing. So very cost-effective way of moving that data into a usable format. So Hadoop is inflexible in storage. So just to go a little deeper in that, because this is such an important thing to understand with Hadoop. So let's just dig into these. When we talk about flexibility, I told you anything you can store on your computer. At some point, you're kind of like, okay, I can put, I store pictures, I store some of the things you don't think about, email, legal documents. We have huge archives of legal documents. Real estate business alone in the U.S. has a 24-page document to 35 pages. Those are standard. How do you pull that information off of there and analyze it for the industry, for the whole real estate industry? How do you analyze all these sensors coming in from the Weather Channel and stuff like that, the Weather Channel, all the weather stations from NCAR, the National Center for Atmospheric Research? So all that data is coming in, and we can use it. We certainly can if we have access to it. So having a place that we can put all that variable data, whether it's a Twitter or an SQL, columns and rows, is very important. You can see we have an Excel document here. Think of that as representing a basic Excel. It could also represent an actual MySQL server poll or SQL server poll. And so when we talk about scalability, I talked a little bit about scalability. As the volume of data grows, new node machines can be easily added and scaled to the Hadoop cluster. I didn't attach a price tag to this. The price tag is that in Hadoop, it's about 1/10 of the cost to have that access and storage. 1/10. So if you're out there and you're getting ready to spend $1 million for your company on high enterprise machines to store this stuff in, and a lot of high enterprise machines don't go past, it used to be, it's kind of changed that you don't really want to go past 5 separate servers. And there's other issues that come in with the way they store data, they move it around. We talked about flexibility, so not only that, but you're storing an SQL server, you're storing a file setup, all this stuff is mishmashed all over the place. Well, this allows you to scale up as much as you need. It's about 1/10 of the cost. So that $1 million is now 100,000. Can you imagine going to your the partners in the firm and saying, hey, look at this great process you guys set together. We need to have this. You said we need to have it. We price it out of $1 million. We can do it for 100,000 in hardware. Pennies on the dollar, 10 cents on the dollar. And we discussed a little bit about fault tolerant. Usually when we talk about fault tolerant, I always think of point of failure. So data stored on HDFS gets replicated automatically onto different data nodes. This brings high fault tolerance when a data node crashes. So what this means is you're throwing commodity machines in there. You know they're going to crash. You know that you're going to get a percentage of them that aren't up to par. Because unlike a high-end enterprise where they're looking at maybe 1 in 1,000 failure, you might be looking at 1 in 100 failure. So you have your enterprise machine, which is going to be your master. There's usually a master backup. So you still have those high-end computers for your single point of failure. You still want those, to sit on top. And we'll look at this a little closer when we dig deeper into the Hadoop file system. But the rest of them, we once took a lab and put together all our laptops and connected them into a Hadoop Spark, and we're able to run code across all the laptops. So in doing that, we went from one computer processing and storing data to, there was like 20 people in there that day. So we had 20 people connected to our service. Now, that's kind of a goofy example because you wouldn't actually do that in real life, because you need the high-end connection that you'd have on a server rack. But you get the idea that we can now leverage multiple computers to do a lot of things we couldn't before, and they're very fault tolerant. One of them goes down and the data is replicated. And it's a distributed storage. We just talked about that. That goes right along with the fault tolerant. It's distributed across multiple computers. So the Hadoop supports distributed data storage and hence allows faster processing of data. And there's a couple little things you need to know about this, which when we dig deeper into MapReduce in just a moment, a little deeper, we'll talk a little bit about the faster processing and what are the limitations and what is coming up in the new market. Hadoop has a robust ecosystem that suits the analytical needs of small and big organizations. These include Spark, Pig, Hive, Mahout, etc. And we talked a little bit about Pig is just a basic query, and Hive, you're looking at your SQL, and I mentioned Apache Spark, and I'm kind of a big touter of the Apache Spark and Mahout. Those are the two, and it's important to know the difference. We might look at, I don't know if we're going to go into Spark anymore on this particular video, but Spark runs in RAM, and Mahout runs back and forth to the hard drive. So Spark runs much faster, but usually you have a higher end RAM on your machines to take it up, where Mahout uses a lower end RAM. So you can imagine if you're going into a company, and that company has already built this data system, and they built it, let's say 6, 7, 8 years ago, before Spark was out, and before RAM has dropped in price, you almost have to run Mahout on there. And Mahout, which does this data analytics, it reads the data from the disk, it puts it in RAM, it does its processing, writes it back to disk, pulls it back off the disk, does its sorting, writes it back to disk, pulls it off the disk, does its reducing, moving things around. And so Mahout uses a lot of hard drive up and down, which slows it down. That's why Spark is 100 times faster usually. But Spark needs more RAM. So again, it comes down to what are you doing with your Hadoop file system? Are you doing a few queries and some data analysts, or are you doing some heavy data analysts across it, in which case you need to make sure that RAM is upgraded. But either way, the Hadoop file system is able to adjust for all that. It's able to be very robust in the way it can address those challenges. And Hadoop stores and processes data on a cluster of commodity hardware, resulting in substantial reduction of cost per terabyte of storage. Cost effective. And I iterated this, it never hurts to say this again. You can store your data and just keep plugging in hard drives. But when you have a huge query, it's going to take a long time. It's got to search through all those hard drives and archives, and if you have tape backup, you have to physically go get that old cassette tape and load it up in the machine, and then it's got to forward it to the location where the data is. So you can imagine that if you have data in a very cheap storage, you're not going to be able to use it very well. A lot of those, it used to be you only stored those for emergencies, for the tax man when he shows up. Hey, what did you do 5 years ago? I don't know, I'm going to go pull it off the data storage. In which case you don't care if it takes you a month to get to it and send it to him because he's the tax man. But now we want to run analytics on it, and it's not cost effective to do that. Most analytics you want done that month or within weeks, because you're going to be basing your business off of it for the next 12 months. A number of businesses I know go in there, they spin up a high-end server, and they run the system, and it might be just 4, 5, 6, 10 terabytes of data they're processing, but because they're doing so much processing on it, they really need that cost-effective way of distributing it across the computer so they get an answer right away. So we're going to dive into Hadoop use case. Before 2008 economic recession, every bank maintained a legacy data warehouse. Now remember, I talked about legacy data where it's warehoused across a bunch of hard drives, and it's really hard to get to. It's great if you're filing taxes and you have a month to pull the data, or you have somebody who can load it up, the old cassettes. So home mortgage details, credit card transactions, and other financial details of every customer was restricted to local database systems. So not only are we talking about very slow retrieval of this data, we're talking about the fact that I might be in Florida, or maybe it's an international bank and I'm in Germany, and I have to call up the Singapore branch and say, hey, I need this data. And so they go and they pull the cassette tape, or if they have it on hard drive, they do a query, their programmer pulls that query, then they have to send it all the way back, and it's a major process. And of course, because of security, you have to sign off on everything, especially if credit cards are involved, and you have to make sure it's secure. So in some cases, they hand deliver that data. It was a serious issue. So banks could not store and process data efficiently. They failed to build a comprehensive risk portfolio for their customers. After 2008 economic recession, most of the financial institutions and national monetary associations started maintaining a single Hadoop cluster containing more than petabytes of financial data. I actually connected up with somebody who works with and I can't say the names of the banks, obviously, but for them to go in there and have their team process that data, remember I talked about that they need to have it processed quickly, they literally, it's about $1 million, that's what they charge to analyze that data across a robust Hadoop file system and load it up across multiple nodes. So Hadoop use case, here's our Hadoop. We're going to, along with the transaction data, it could also store call records, email, chat, and web logs. And as you can guess, if we're already doing storing call records, they might even be restoring recordings, photographs. We didn't even touch photographs in this. So it's a huge amount of data that's now being stored across multiple different businesses for different uses. Data is analyzed to perform sentiment analysis, text processing, pattern matching. The sky's the limit on this. There are so many different things it's being used for nowadays that we could spend an hour just discussing all the really cool, from scientific to business uses for Hadoop case. So JP Morgan is a giant in banking and financial services in more than 100 nations. And now remember, before, all this data was being stored, Singapore was stored in Singapore, Germany was stored in Germany, the US probably had a couple different data branches storing the data for JP Morgan. You actually would break it up into the eastern and western side kind of thing. And so with over 150 petabytes of data, 30,000 databases, 30,000! Could you imagine trying to pull 30,000 databases from around the world so that you could do analysis on it? Could you imagine pulling 30,000 different databases to do data analysis on it? 3.5 billion log records. Data is the oil for JP Morgan. That's how they know where they're going to invest in. Who are they going to trust to give loans to? How are they going to leverage the loans they have in their investments? All of that stuff is, the term, the oil for the industry. That is their gold. That is what they use to make their business. So the answer, of course, is Hadoop. Storing vast volumes of unstructured data allows the company to collect web logs, transaction data, social media data. Just about everything you can imagine that goes into JP Morgan Chase & Company is now put into a Hadoop file system. And Hadoop uses, we use the Hadoop framework for risk management and detecting fraud transactions. I didn't even mention that in all this. Fraud is huge. If you can cut your fraud, that is pure profit for a company if they can cut that fraud in half. If you have billions of dollars going out in fraud and you cut it in half, you just made $500 million. That's the kind of money we're talking about with JP Morgan and Chase in a large company like this. So what is HDFS? Now, we've already given you a definition earlier, but let's just pound it into you a little bit, make sure you remember it. HDFS, Hadoop Distributed File System. That is the HDFS. It is the storage layer of Hadoop that stores data in multiple data nodes. And so here we have our big data. We're going to dig a little deeper into the structure, what's going on, and you have your data node 1, data node 2, data node 3, and data node 4, and so on. In HDFS, data gets divided into multiple blocks, and the blocks are stored on multiple nodes. So what this looks like is if you have 300 megabytes of data, that data is going to come up, and we're going to split it into, the default's 128 megabytes. You can make that smaller or bigger depending on what the need is and how the data is coming in. So if 300 megabytes of data would come in, and we would store it 128 megabytes on one node, 128 megabytes of another, and 44 megabytes on a third node. So each block of data is stored on multiple data nodes and by default has 128 megabytes of data. And then we have the master node, we have the crown, and you have your name node and you have your secondary name node. The name node is the master server. The secondary name node is the backup server. Now these are going to be enterprise computers. So when you're creating an HDFS, I've seen ones without them. Generally when you're talking these larger businesses that are going to invest in 10, 20, 100 computers on their Hadoop file system, these are going to be enterprise machines, because if the name node goes down, and you want to make sure that secondary name node is solid, and you want to make sure the name node doesn't go down. That's your point. Those are your points of failure on here. Your single points of failure. This is what is the important part. And the name node and the secondary name node are the master daemons. This is where your daemons, not demons, but daemons. This is where your master daemons are. And so when we look at the name node and what's coming out of the name node, we have the metadata in disk. You have your edit log, your FS image, and your metadata in RAM, metadata name, replicas, home, food, data 3. So the name node holds metadata information about the various data nodes, their location, the size of each block, etc. All the information it needs to access that data. And then it helps to execute file system namespace operations, opening, closing, renaming files and directories. And so when we look at the secondary name node, it again has the edit log and the FS image. So the secondary name node server is responsible for maintaining a copy of the metadata in disk. And we dig a little deeper here as far as terminologies. We have slave, that's your data nodes. Data nodes are the slave daemons that store and maintain the data blocks. And the data node reads and writes client's request and performs block creation, deletion, and replication on instruction from the name node. And remember, your client is, if you're the programmer who's pushing data in or pulling data off of here, the computer you're putting those commands on is the client. That's usually referred to as the client. You're sending instructions, and those instructions go to the metadata ops and into the name node. And then it sends all that information out and it comes back to the client machine. And so we're looking at the actual name node operation. It goes in and the data nodes read and writes the client's request, so it's going through the name node, and performs block creation, deletion, and replication on instruction from the name nodes. And you can see here we have our block ops that come in from the name node, and then it tells the individual nodes what they need to do. And then we have a response from the name node, what the operation was successful. That goes back to the client. And you can see here the client, when it reads and writes it, when it reads the data or writes the data, it's coming directly from the client. So the client machine is able to send that directly to those specific nodes. So let's look a little closer at the Hadoop file system write. We have our client, that's the programmer and the computer. Where can I write and store my data? That's our, he asked the master, or the king in this case. And then the data is split into multiple blocks on 128 megabytes each. So if you're going to write it, it's going to split that up, or if you're reading it, it's going to look for those 3 blocks. And it finds the data nodes available. So when we're looking at writing to it, it says, okay, these 3 data nodes have room on them. Let's go ahead and put that 300 megabytes, all those 3 different splits onto those data nodes. And then you write the first block of data to A3, B2, and B4 in this case. This is like, obviously it's going to be different. If you look at these as rack 1, rack 2, rack 3, I always found this interesting, is 2 of those nodes are usually on the same rack, and that has to do with the speed of replication. And then a third one is on a different rack, which is for security. If one of the racks goes down, you don't want to lose the data. Similarly, the other 2 blocks are written on different data nodes. And you can see here where it comes across, and now those are written on different data nodes. Sorry about that. And we talk about replicated data. The default is to replicate it thrice on 3 different data nodes. And this is part of our fault tolerance. If we're expecting 1 in 100 of these machines to go down, we want to make sure the data is not lost. And similarly, the other 2 blocks are written on the different data nodes. And so each of those blocks is now replicated 3 times. So now the client comes up and says, hey, I want to read my file, and it goes to the king or the master, and the master goes out and finds the data nodes to read from. And then it comes back and says, hey, read data from A2, A3, B1. And of course that goes in and pulls those data directly from those nodes onto the client machine, so now you can look at those data. Or you can process those data on those nodes and then reduce it down to something that you can handle coming across. So importing data to the Hadoop file system. This becomes a big deal. We have relational databases, so RDBMS and a data warehouse. Think of this as your, if you're in a company, this might be the sales computer, or this might be, we're talking about JP Morgan and Chase. Each of their branches is going to have their own server and their own RDBMS where they're storing all that data for that day's business. And so what's used on those is your Sqoop. Sqoop is used to import data from relational databases onto HDFS. And usually you think SQL Server or MySQL Server when you're looking at this, the SQL. Flume is used to import streaming data from sensors and web servers onto the HDFS. And you can see web server, you can see sensor, streaming data. This would be usually your non-SQL, your Twitter accounts, your social media. These are things that don't fit into a neat column and row setup a lot of times. Now, I mentioned earlier MapReduce. And MapReduce is very important, not just for the actual MapReduce in Hadoop, but in programming and development. Anything you do, you really need to start thinking MapReduce, because there's a lot to do with how the data is processing and how to maximize your resources. So MapReduce is programming model to process large data sets in parallel on different nodes. And you can see here, here's our master node. Data is processing simultaneously on different slave nodes. This would be the crown that we looked at before. Instead of a guy behind a computer, it'd be the king of the Hadoop file system. And so when we look at this, we want to be able to process, we have like our slave node 1, 2, 3, and 4. Process something simple like an average across that. That becomes a big question, because you can't, you have to sum up all the numbers, and then you have to divide by the total number underneath. So there's a lot of steps that go into processing the individual slave nodes and then bringing that data together. And that's what MapReduce is about. So let's look at the MapReduce workflow. We start with our map tasks. In map, think of it as a single line if you're in SQL and you pull a line of data from a table. Maybe it's a single document if you're working with documents. This is the process that you're mapping across. You're taking that data and transforming that line of code, that piece of data, to what you need. Then you have a shuffle and sort. This is where we take that mapped data and we move it to the server it needs to go to. We move those pieces together to the pieces that they're going to be set on. So if you're counting like how many times was the word Google used in a bunch of documents, it might go through each document and count Google and then send those totals to all the other into one server so it could then add them together. And then reduce. Reduce is where we take all that information we shuffled together and we reduce it to something we can use as an end user. If I send you a terabyte of data and you have to look at it, it's not going to mean anything to you. You need a single graph or something very simple that as humans we can take in and say, oh, that's the average, or that's the means, the median, the whatever, minimal, max, all those different data analysis things that come out of this data. And that's the final output. So we're going to reduce it to something that, as to that single line that has meaning. So as we go through MapReduce, let's look at an example. We have a square red triangle, blue circle green, square green triangle, white cube blue, cube yellow, circle red, cube blue. So we have these different lines that are describing random squares and colors and things like that. Let's say that's our input. You might think of this as like a Twitter account describing the politics of the day. We got an orange circle and whatever. So this is an input coming in. And so the map function is going to look at this and it's going to say, okay, let's take this input, the square red triangle, blue circle green. So this might be one Twitter post, and it's going to map it out. And it's going to say, okay, square red triangle, blue circle green. And so part of the map function is we might want to split this into two groups for whatever reason. In this case, we're just arbitrarily splitting it in half, the first half and the second half. It's still a map function. This is everything we're doing on one set of data coming in. And so we have square red triangle, we split into two groups. And then we take again, this is all on one line. For our MapReduce, we're mapping these entities into something meaningful. And in this case, we're going to map it to square equals 1, square equals 1, red equals 1, green equals 1. And this is always a strange concept. Why would I have square equals 1, square equals 1? Why not have square equals 2? Sometimes you have square equals 2, and sometimes it's easier to count the numbers by doing square equals 1. As you dig deeper into the code and whatever system you're using, a lot of times it handles that particular concept to maximize the processing. But when you're talking about counting words, that's usually what it looks like. Square equals 1, red equals 1, blue, white, blue again. So this is still the map step. Why? Because this is everything you can do to one line or one format coming in. In this case, we mapped it into 2. We split it into 2. So now we have 2 different entities that we mapped to, and one of them has square, square, and so on. The other one has cube, hexagon, and so on. And so now we take the information generated from what we just did, we group it together. So this is the shuffle step. The shuffle step actually takes up the most resources when you're doing a MapReduce program, because it is physically moving information from one node to another. And in this case, we take the square 1, now we have square equals 1, 1, red equals 1, triangle equals 1, 1, and the same thing below. And we shuffle that again and merge it again. So again, we're doing a shuffle and sort step here in the middle until we have all our squares and reds, and all of them are 1, 1, 1, 1. And then we get down here, we're still shuffling and sorting it down to blue, circle, cube, and green, and then we reduce that down to something we can read. We can read blue 4, circle equals 2, and so on. So for simple counting of words, you can see how these steps come together. And one of the things I want to point out, I mentioned Spark versus MapReduce. MapReduce, as we go back here a little bit, MapReduce is in Java, and it is one of the underlying functions that runs on Hadoop file system, where Spark does the same thing in RAM. What that means is if you have a very low amount of RAM and a huge file system, when we map this map function, which we split into 2 groups, then writes those 2 groups back to the hard drive. Why? Because you don't have a lot of RAM to store it. That's what MapReduce does in Hadoop. And then when it gets to here, it takes those 2 entities and continues to map them, and then writes that answer to the hard drive, because it can do that. It can do that very easily. So you got to read and write, and so on. And each of these steps is a read and write to the hard drive in the MapReduce. That's a big difference between Spark and Hadoop. With Spark, you have a heavy amount of RAM, and you're reading it into the RAM, and it stays in the RAM. So it's always important to know that difference going on here between MapReduce. The thinking about it is the same. Usually we don't think, hey, I want to do square 1, square 1, square 1. I don't think of that when I program, because I'm looking for the final answer. I'm looking for, hey, how many squares do we have? We had 3 squares. But that is the kind of thinking you have to go through when you're processing a program through MapReduce. So let's go ahead and jump to Yarn. And I always love the title of Yarn. Yet another resource negotiator. Yarn was introduced in Hadoop 2.0 to solve the issues in Hadoop 1.0. MapReduce 1, such as scalability, availability of nodes, resource utilization, and etc. So it used to just be MapReduce, the backend MapReduce, and you'd write your code, but there's issues that would come up. So Yarn is a cluster resource management layer of Hadoop that schedules jobs and assigns resources to running applications. And so you can see here we have our memory, we have our CPU, we have our RAM. So you have from hard drive to RAM to how much processing power you have. The Yarn handles those loads and figuring out where to best assign them. So from a client perspective, the programmer comes in, or the admin comes in, submit a job request to our resource manager, and as the client submits an application to the resource manager, it comes in as a job submission. And then you come over here and you have your node manager for each of your computers, and then it has this container and its app master. So your container, so you can see it's splitting up the different tasks on, you can look at those each as being an individual computer, and it's splitting up those tasks into the different parts to easily take care of. So the node manager sends a status to the resource manager. Application master contacts the related node manager, and the container executes the application master. So back to our bank case study. You own a virtual bank that is generating a lot of customer transaction data and uses the RDBMS to store the data. Again, these are commodity machines, you're paying a lot of money for them. But the bank's data is rapidly increasing, and RDBMS has become inefficient in handling such large volumes of data. And here's the other thing about RDBMS. You don't just add another one onto your system, you upgrade it. So instead of adding one computer at a time, you go from a high-end Dell or IBM server to a Sun computer. to whatever the next one is. And you start to realize that those jumps leaves you with old computers for one, and they're really expensive. When you go from an increase of 50% of computing power, the price tag is a lot more than 50%. You need a solution to move your bank data from traditional RDBMS to more flexible and scalable data storage. What if I use Hadoop Distributed File System, the HDFS, to store the data? HDFS can easily store large volumes of data, so let me use Sqoop to move all the bank's data from the RDBMS into the HDFS. So again, we have our high-end server, and we want to move that data over so that it's in an affordable storage that we can still process it. This will also allow us to analyze customer data using Sqoop commands. Now let's see how to do this. So for this demo, we're going to be using the Oracle VirtualBox Manager and the Cloudera Quick Start. And I'll go ahead and start this up, bring up our Quick Start window, and I've already got it actually started up on here. And it should open up once you've installed it. And if you need help with that installation, we do have a previous tutorial we put together on that. So put a note down there. I believe you need a minimum of 12 gigabytes RAM is what it requests. You can kind of get by with under that, but you'll run into problems. And it's also, I'm on the professional machine, you have to do some extra settings if you're not. So it can be a little challenging getting it set up, but once you're up and running, it's very easy to use. There's other sources too, like AWS. You can spin up a server on there. So there's a lot of other options too to play with the Hadoop file system and get into it. This is of course a single node, and I've opened up, here's my Cloudera running, the VirtualBox on top of my Windows computer, and the Cloudera in this case is Linux. I believe it's CentOS. It might be Red Hat or Ubuntu. I'm pretty sure it's CentOS on here for this one. And when it comes up, the first thing you see is by default Cloudera put this together, is it comes up in a browser window and you have your Hue editor. And I can do just about everything in the Hue editor, which is really nice. I can go into the query editor. We have Impala Hive, all the different tools we were talking about, Spark, MapReduce, and Sqoop. So I can now come in here and put my Sqoop commands. And I can also click over here on the left. Right now it's highlighted underneath the Hadoop file system. These are actual files from a previous demo, departments dep1, dep2. So as we create folders in here, you can see them right here in the Hue query. Now if you've been in previous demos of mine, you know that I like to do it in the terminal window. The terminal window usually has a faster response as far as submitting. This is like there's like an added internet connection even on this single node coming from here because of the way it's set up. When you're doing a remote client, probably less of a difference. You could probably use either one. And it just depends on what you're working on. And so I've got my terminal window up here. This is on the Linux system. So this is in Linux. All your Linux commands like list. Okay, so we can list, and you can see right here are some files on the system just like you do a directory in Windows. And then I'm going to have a second window open. And the reason I'm doing two windows is the second one is going to be for doing MySQL Server. If we're going to scoop some data into our Hadoop file system, it's important to have MySQL Server up and running. In this case, MySQL Server, we have to have -u for the user. It's going to be root. That's how Cloudera is set up. And the password. Now, a lot of times you just put -P and it prompts for the password. Not a good idea to share your password, especially for a MySQL Server if you're in a large company. But in Cloudera, it's a quick start. We're just playing with it. I think this is even, well, maybe, I don't think you can even get to my computer into the VirtualBox through my external firewall. So even knowing my password wouldn't do you any good. And if you did get in here, what would you get from it? Not much. So this is now MySQL Server right here. And I've now entered in, you can see my SQL prompt. And we're just going to do a simple create database, and we'll call it bank, followed by the semicolon. So this is a MySQL Server command. And let me up it one more. View, zoom in. There we go. Make it a little bigger so it's easier to see. So once we're in here, we create our MySQL Server. We can actually show databases, and you can see in here bank at the top, and then we can come in here and we're going to go ahead and use bank. So any commands we have for SQL are now set to bank, the bank database. And let's go ahead and create a couple tables in here. So I had somebody else put this together. So we're going to create a table called bank_loan. There's our bank_loan, and it's going to have the loan ID, which is an integer, which can't be null. We're going to have a user ID integer, also can't be null. We have, what is this? Last payment, kind of skips off the side here so you can't see it on the side, but that's last payment. So we have last payment, which is going to be a date. Payment installation is a double. Loan amount pending, double primary key, loan ID. So there's our schema for this particular table. Go ahead and hit enter. And then let's create another table. And we'll go ahead and quickly paste that in. And this one is going to be credit card. And so we have credit card number, the user ID, the maximum credit, outstanding balance, due date, and the primary key is a credit card number. And if we go show tables, there it is. Bank loan and credit card are two tables. And let's go ahead and insert some data in here. Hopefully this will process okay. You never know when I get data, sometimes the auto formats on our text editors come through. So I'll have like I had to replace the quotation marks all got messed up and stuff like that. But you can see here the format, pretty straightforward. We have our loan ID, we have our user ID. So our loan ID is the 101, 201, payment installation, all those different things that are going into this particular table, the bank loan. And you can see right here just listed loan ID, user ID, last payment, etc. This is all the data that's going in there. And you end it with a semicolon. That's common in a lot of the online scripting so that you know to actually execute all these lines. We'll hit enter. We said, okay, good. Yay, we got it in there. Didn't make any mistakes. And the same thing if you request any of this information. Make sure you're aware that sometimes text documents reformat some of this stuff. And so we're going to insert into our credit card number, user ID, and so on. You can see right here, it now goes in there. And we can into the MySQL. So this is on the MySQL tables right now. And we've uploaded this into our MySQL database. So you can think of that as being the enterprise machine. That's the company's computer that they spent a lot of money on and they've upgraded and spent huge amounts of money on. And the bank's using it to store that bank's information. And we're going to skip over to our other window, which is just a straight Linux prompt. And we'll start doing our Sqoop commands in here. And so with Sqoop, you can actually think Sqoop list databases. This is a Sqoop command. Now I could have done this in MySQL and listed the databases or show databases. But in Sqoop, we have list-databases. How are we connected? We're connected through the JDBC. And then a lot of times you'll see instead of MySQL Server, you'll see localhost. But this is the Cloudera direct one, and the newer one is MySQL Quick Start. 3306 is the port number. Username we saw before is root. Password is Cloudera. And again, I usually don't put the password in here. You do like well, with Sqoop, if you're doing an automated system, you do at some point have to put a password in there if you're automating it. But in this case, we're just doing queries, and you don't usually want to put your password in there. And so you'll see it go through everything, and sure enough, here's all of our here's our bank and all our other databases. And this was run through Sqoop versus running it through the MySQL. And then we go ahead and take a look and see what's in there. Sqoop list tables. So you start to see a standardized series of commands. List databases, list tables. Here's our connection, and we've added on to the connection bank, so it knows which database to look in. And again, username and password Cloudera. And because we're in the Linux, we don't need the and symbol on the end. This is the basic Linux terminal. It's not one of the scripting shells. And we'll hit enter on here. And you can see in here has bank loan and credit card, the two different tables we created in the MySQL. And then that was a lot of work to get to here. Boy, we created a database in MySQL. We jumped around. Now we're actually just going to scoop some of that data in here. And so here we go. Sqoop import is the key word. Same connection with the bank on the end because we're going into the bank. We have our username, our password, and then we want to tell it what table to go into. So we want to scoop into the table credit card, or from the table credit card. And this is going to scoop into our Hadoop file system. And let's go ahead and hit enter in there and see what it does. And we have an error, unfortunately. Easy to fix. And this again is, we work as a team. So when they send me over the commands, sometimes something gets reformatted. And you can see here under password, instead of a dash dash, it has some kind of other character that got formatted funny coming across. So we'll go ahead and run this. And sure enough, it goes through and it's going to import that data into our Hadoop file system. And so this is going through, you'll actually see here's our MySQL Server request, and then it goes through the reduce, and it's just being mapped. When you're bringing something in like this, you'll see map pop up in here because we're not reducing the data, we're just mapping it it straight into Hadoop. So it's just a map process putting it in there. And then once it's done, it'll take just a moment to finish here, we can simply use the Hadoop file system. This would look familiar because with Hadoop you use ls or -ls, -ls. It's going to be under the user Cloudera. So if I run this, we should now see a file. We just brought in the credit card file, and sure enough, there it is. Credit card is our top one. We just brought that in. And we can also flip over to Hue. This is always kind of fun to do. And when we flip over to Hue, you can now see credit card up here. And note, there's a little, it's hard to see on this. I should probably zoom in. There's a little refresh button. So you got to make sure you hit that little refresh button before the credit cards show up on here. And once we do this for the credit card, let's go ahead and import our bank loan. So right there's our table, bank loan. That's where it's coming from. Password Cloudera, and it's an import. And we'll hit enter on here. And this will bring in our bank loan table into our Hadoop file system. And again, we can go ahead and do our Hadoop file system -ls for user Cloudera. That's where we put the data in there. And you can see when it comes up here, we have bank loan and our credit card. So now we have both of these imported. And we can also go into Hue, just flip on over here, hit the refresh button, and now we have bank loan and credit card. And this is just a, like I said, Hue you can use just like you use a terminal window, jumping back and forth. And then we can do something kind of fun, Hadoop file system. And if you remember, cat is used in Linux. It's also a Hadoop file system. You have to remember where you put everything. So user Cloudera. So we're going to go ahead and just go into here, Cloudera, and then I want to know, let's go back into our bank loan, and then I want to know part. We'll do part star. Star is a wild card. So this is every file that begins with the word part under bank loan. And this is going to pull the data out of them. And you can see here's the data. And it's just what we put in there, the 101, 201. This was what the bank loan had, the bank loan number, had the customer ID, the date, and so on. And this is kind of interesting. Let's go ahead and take this, and I just want to do, instead of looking at the bank loan, what's actually in that? What's going on in here in our bank loan? So let's do a list of there, our Hadoop file system -ls. And you can see here underneath bank loan, it's actually partitioned into part-M000, 001, 002, and so on. So each of those lines are partitioned into their own subfolder under the bank loan. Don't really need to know that too much. It just helps when you're working with the Hadoop file system to realize that it will look at a folder and then it looks at the content of that folder almost like it does a file, which is kind of a cool thing you can do with Hadoop file system. And then we can also go back up to our bank loan line. You just use the up arrow to page through whatever you just typed in. And we'll do credit cards. You can also see the credit card on here. And that will print out all those files, all the different information on the credit card. So here's our credit card number, and the different scheme amounts to go with it right here. And let's do another one like that, but this time from the bank loan. And again, let's go ahead and set M3. So this is all we've seen before is your Sqoop, your import. We're connecting to MySQL server. We're connecting specifically to the bank database, user, password, table, bank loan. So we're going to do the bank loan. And we want to go ahead and do where. In this case, let's do where payment installation. So our payment installation equals, this is 15,000 a year, maybe not the US. I don't know, it's a hefty payment. And we'll do a target directory because we want to tell it where to go. And we'll put this into user Cloudera, and we'll call it loan 2. So again, we're looking at pre-processing data coming in and just selecting the data we want to put in there. In this case, where the loan payment is 15,000. And we'll simply view the data. And because I'm a lazy typist, I go ahead and hit the up button twice. I know it's in loan 2 directory. And we'll use a Hadoop file system -cat, and then our Cloudera loan 2, and then part asterisk for the wildcard. As you can see here, it imported the one line with the $15,000 payment going on it on this particular loan. And likewise, it's always fun to just up arrow it. Here we go. So we had our Sqoop, import, connection, passport, our table. And let's go ahead and change this a little bit. And instead of bank loan, to use the back arrow, since we use the arrows to get there. And instead of this, we might go back to our credit card. and we'll keep it as an M3. And instead of the where statement, let's change this. Let's change this to a date, because now we want to track all the due dates coming up. And so we can simply come in here and do due date, and we'll set it. The due date is less than. I have to remember to change that to double brackets, because what we're going to do is we're going to do the actual date. 2018, what was it? Let's do 06/20. There we go. We're going to single. And then we'll do the target Cloudera again, target directory user, and we'll call it credit 1. So we're going to put it into a different location. There we go. If we run that, we're going to sort those out. We're going to set all the due dates that are less than 2018 06/28. And then we simply do the Hadoop file system cat command. And in this case, we did what? User Cloudera, and we put underneath credit 1, and we want our part star. And that should pull up our files in the 3 different parts, because we did MapReduce to 3 different parts, and there we go. We have our records coming up from our credit card 1. And then let's do 2 more commands. Let's start by getting the record of a customer who has minimum payment installation and maximum loan amount using the Sqoop eval command. And so when we start this one, we have Sqoop, but we have a new command, eval. And then from this part, here's our what we already had before, connect to our JDBC with that information, the bank database, username, root, password, Cloudera. And so we're doing an eval, and the first thing we need to do is we need to set up a query. So we'll call it a query, and this should look familiar. Select star. So we're selecting everything. We're minimum payment installation. There we go. Always double check your typing on those. And we want the max loan amount. There we go. Max loan amount pending from bank loan. So there's the table it's coming from. And we'll go ahead and run this. And it comes up as like a query on here. So you can see loan ID, user ID, last payment. Of course, this is really wide, and I've because I have the view so big, it's hard to read. So if we did run the same thing, let me just, in fact, let me back out so you can see what this looks like if I ran this with a smaller font. And actually just open up another window and run it. And you can see right here, it comes up and it has, because we're doing a query, it makes a nice little SQL query and nice little columns and rows for you to read. And let's do one more eval. And this should look familiar, you know, Sqoop eval. Here's our connection. Here's the query command on here. And in this one, we're going to do a select, and let's just select the sum. So we can do that. That's a standard SQL kind of setup on here. And you'll see a lot of similarities. There's some things that are not going to be in the Sqoop commands, but when you start looking at this, you're going to see how you start seeing how that query works. And we want to just sum the outstanding balance from credit cards. And there we go. We have $737,000 outstanding from credit cards. So that puts a wrap on our basic Sqoop demo that we had going on here. And you get a quick view of the Hadoop file system. One of the things I didn't do is go back into here in Hue and do the refresh. And if we do the refresh, it's kind of small on the font here, but you start seeing there's our loan 1, our credit 1, all the different things, credit card, bank loan, all of this stuff added in. At some point, you have to decide what you're going to keep. Obviously, this is just an example, but I'd be very careful about just dumping new data into a data warehouse like this, because then you get a lot of replication. But it's important to know how to bring that data in and how to do some basic evaluation using the Sqoop commands. So, quick key takeaways. The need for Hadoop. We covered all the different data sources coming into the Hadoop file system. We talked about what is Hadoop and how it goes across multiple nodes and servers. We discussed a Hadoop use case with banks. What is the Hadoop file system, or HDFS? Very important, MapReduce workflow. The more advanced you get, the more you start appreciating how to think MapReduce. And we did a bank case study, and you can see from our Cloudera example of using Sqoop how that might not be just one database you're scooping in. That might be something that runs every morning. So we might have one of our monitoring systems come in and run this script to bring in the data for the day and scoop it in from Singapore, from the US. So the daily stuff is now coming into the warehouse so it can be used. So don't think it's just coming off your computer. This is actually, Sqoop is usually used in a much bigger picture. So that wraps it up for us today. Thank you for joining us. Again, my name is Richard Kirshner with the Simplilearn team. For more information, visit www.simplilearn.com. Feel free to post in the bottom under YouTube. We do have somebody who monitors us. And join our YouTube channel. Again, thank you for joining us. Happy learning. Get certified. Get ahead.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.